How many main crystalline lattices? How many main crystalline lattices? Three. Three main crystalline lattices: body center cubic, face centered cubic, and hexagonal close packing. Body centered cubic, face centered cubic, and hexagonal close packing. What does the microstructure of steel depend on? What does the microstructure of steel depend on? Well, the microstructure of steel depends on chemical composition, cooling rate, heat treatment processes, initial microstructure, mechanical working, temperature of heat treatment, and time at temperature. How does chemical composition affect the microstructure of steel? How does chemical composition affect the microstructure of steel? The primary element is iron, with carbon being the most important alloying element. Other alloying elements such as manganese, silicon, chromium, nickel, molybdenum, and vanadium also play significant roles. The amount of carbon and other alloying elements determines the types of phases that can form. The primary element is iron, with carbon being the most important alloying element. Other alloying elements such as manganese, silicon, chromium, nickel, molybdenum, and vanadium also play significant roles. The amount of carbon and other alloying elements determines the types of phases that can form. How does cooling rate affect the microstructure of steel? How does cooling rate affect the microstructure of steel? Well, the rate at which steel is cooled from the austenitizing temperature, where the steel is in the austenite phase, has a profound effect on the resulting microstructure. The rate at which steel is cooled from the austenitizing temperature has a profound effect on the resulting microstructure. Slow cooling generally leads to the formation of equilibrium phases. E- Equilibrium phases like ferrite and pearlite. Slow cooling generally leads to the formation of equilibrium phases like ferrite and pearlite. Rapid cooling or quench can produce martensite, a hard and brittle phase. Rapid cooling or quench can produce martensite, a hard and brittle phase. Intermediate Intermediate cooling rates can lead to the formation of bainite. Again, the rate at which steel is cooled from the austenitizing temperature has a profound effect on the resulting microstructure. More specifically, slow cooling generally leads to the formation of equilibrium phases like ferrite and pearlite. Rapid cooling can produce martensite, a hard and brittle phase. Intermediate cooling rates can lead to the formation of bainite. How do heat treatment processes affect the microstructure of steel? How do heat treatment processes affect the microstructure of steel? Annealing. Annealing means heating and slowly cooling steel to produce a soft and ductile microstructure, usually consisting of ferrite and pearlite. Normalizing. Heating steel above its critical temperature and then air cooling, resulting in a fine polyistic structure. Quenching. Rapid cooling to form martensite. Tempering. Reheating quenched steel to slower temperature to improve toughness by reducing the brittleness of martensite. As tempering. Quenching to an intermediate temperature and holding to form bainite. How does initial microstructure affect the microstructure of steel? Well, the starting microstructure of steel before any heat treatment or processing can affect the final microstructure after treatment. For example, coworked or rolled steel has a different initial microstructure compared to annealed steel. How does mechanical work affect the microstructure of steel? Processes such as rolling, forging, and drawing can define the grain size and shape of the microstructure, affecting mechanical properties. Cold working can introduce strain hardening and change the dislocation structure within the steel. Processes such as rolling, forging, and drawing can refine the grain size and shape of the microstructure, affecting mechanical properties. Cold working can introduce strain hardening and change the dislocation structure within the steel. How does time of heat treatment affect the microstructure of steel? How does time of heat treatment affect the microstructure of steel? The temperatures at which the steel is heated and held during various heat treatment processes influence phase transformations. Higher temperatures typically lead to coarser grains, while lower temperatures favor finer grains. The temperature at which the steel is heated and held during various heating processes influence phase transformations. More specifically, higher temperatures typically lead to coarser grains, while lower temperatures favor finer grains. How does time temperature how does time at how does time at temperature affect the microstructure of steel? The duration of which steel is held at a particular temperature during heat treatment affects phase transformations and grain growth. The duration of The duration for which steel is held at a particular temperature during heat treatment affects phase transformations and grain growth. Longer times can lead to coarser microstructure, while shorter times promote finer structures. Which heat treatment produces a soft and ductile microstructure? Which heat treatment produces a soft and ductile microstructure? Annealing. Annealing, the metal is heated to a specific temperature with a range 500 to 900 degrees Celsius. It is held at that temperature for a sufficient period to allow crystallization. It is then cooled slowly, usually in the furnace, to increase ductility and reduce hardness. Annealing. The metal is heated to a specific temperature within the range 500 to 900 degrees Celsius. It is held at that temperature for a sufficient period to allow recrystallization. It is then cooled slowly, usually in the furnace. So, this method can increase ductility and reduce hardness. Which heat treatment produces a fine polycystic structure? Which heat treatment produces a fine polycystic structure? Normalizing. The metal is heated to above its critical temperature, 800 to 950 degrees Celsius. It is held at this temperature for a period. It is then cooled in air. So the result is refined grain structure and increased toughness. What's tempering like? The hardened metal is reheated to a temperature below its critical point, 150 to 650 degrees Celsius. It is held at this temperature for a period. It is then cooled, usually in air. The result is reduced brittleness, improved ductility, balanced hardness and toughness. What is the role of carbon in steel? Carbon increases carbon increases hardness and strength through the formation of iron carbides. What is the role of manganese in steel? Manganese acts as a deoxidizer, deoxidizer to remove oxygen from the molten steel, improves strength and toughness by forming manganese sulfides and combining with sulfur to reduce brittleness, enhances wear resistance. What is the role of silicon in steel? The oxidizer. This also acts as a deoxidizer, strength and hardness, increases strength and hardness without significant affecting ductility. Magnetic properties improves magnetic properties in electrical steels. What is the role of chromium in steel? Corrosion resistance. Key element to corrosion resistance, especially in stainless steel, equal or greater than 12% chromium. Hardness and strength. Increases hardness and strength, especially in high temperatures. Wear resistance. Enhances wear resistance. What is the role of nickel in steel? Toughness. Increases toughness and impact resistance, especially at low temperatures. Corrosion resistance enhances corrosion resistance. Strength contributes to high strength and toughness in alloy steels. What is the role of molybdenum in steel? High temperature strength improves strength at high temperatures. Hardness and toughness enhances hardness and toughness. Corrosion resistance increases resistance to pitting and crevice corrosion. What is the role of vanadium in steel? Grain refinement refines grain structure, leading to increased strength and toughness. Hardness and wear resistance forms vanadium carbides that increase hardness and wear resistance. What is the role of titanium in steel? Grain refinement refines refines grain structure, improving strength and toughness. Stabilizing element stabilizes austenitic stainless steels by preventing chromium carbide formation. What is the role of aluminum in steel? Deoxidizer acts as a deoxidizer in steel making, removing oxygen from the molten steel. Grain refinement helps in refining the grain structure, leading to improved strength and toughness. Nitriding forms aluminum nitrides. What is the role of aluminum in steel? The oxidizer acts as a deoxidizer in steelmaking, removing oxygen from the molten steel. Grain refinement helps in refining the grain structure, leading to improved strength and toughness. Nitriding forms aluminum nitrides, which enhance surface hardness through the nitriding process. What is the role of copper in steel? Corrosion resistance enhances resistance to atmospheric corrosion and improves the weathering characteristics of steel. Strength increases strength, especially in low alloy steels. Aging contributes to age hardening in certain gray steels, steel grades, leading to increased hardness and strength over time. What elements increase hardness and strength? Carbon, silicon, chromium. What elements increase toughness? Manganese, nickel, molybdenum, vanadium, aluminum. What elements act as the oxidizers? Manganese, silicon, aluminum. What elements refine the grain structure? Molybdenum, vanadium, titanium, aluminum. What elements enhance corrosion resistance? Chromium, nickel, copper. Which element enhances pitting and crevice corrosion resistance? Molybdenum. What elements increases wear resistance? Manganese, chromium, vanadium.